So standard conditions, also known as standard temperature and pressure, or STP for short, refer to a specific pressure and temperature, and this is useful for making comparisons between gases because the temperature and the pressure have a direct effect on the volume of the gas. So standard pressure is 1 atmosphere, which is the same as 760 torr. You need to know what this pressure and temperature are. So if I don't have a reason for why something is, I make up a reason that makes sense to me. And does it really matter if it's the actual reason? No. It helps me remember what it is. So standard pressure. What would be an easy pressure to have? Atmospheric pressure, the same pressure that's in the room that you're in, right? If you have a gas container and you put a manometer on it and you arrange it so that the level of the mercury is the same on both sides, then you know the pressure inside is the same as the pressure outside. No special instruments or anything required. So that's convenient. Standard temperature is 273 Kelvin or 0 degrees Celsius. This is convenient because this is the temperature of an ice water bath. Water freezes, melts at 0 degrees Celsius. So if you have your gas container and you submerge it in a big container of ice water and wait a few minutes, even without having a thermometer, you know what the temperature is. So that's a convenient temperature. Room temperature we use a lot, but room temperature can vary widely, right? Like the room temperature in here was 63 Fahrenheit earlier, and sometimes it's been 85 Fahrenheit. So that's a huge difference. So that's STP. Anytime you see at STP, they are telling you the temperature and the pressure that way. We've talked about molar masses. A molar mass is the mass of 1 mole. A molar volume is the volume of 1 mole of gas. And we do that at STP so that we can compare them. So let's calculate the molar volume of 1 mole of a gas at STP. Wait a minute. So to calculate the volume of 1 mole of gas at STP, we're going to use the ideal gas law. So the ideal gas law, PV equals nRT. We want to find the volume. So we rearrange the equation. The volume equals nRT over P. So the amount of gas is 1 mole. So 1 mole of gas. And the ideal gas constant is 0.08206 liter atmospheres per mole Kelvin. The temperature is 273 Kelvin. I just can't do that. It's 273.15 Kelvin. This bugs me. And the pressure is 1 atmosphere. This 1 mole is exact. This 1 atmosphere is exact. And the 273.15 Kelvin is, well, 5 sig figs. So we do the math here. We have 0.08206 times 273.15. So the volume equals 22.414689 is what my calculator says, and that would be liters. So doing it this way, we've got 4 significant figures, and so it would be 22.41 liters. For whatever reason, that's often rounded to 3 sig figs. I guess, the 1 is pretty close to 0, right? So it's usually rounded to 22.4. That's the volume of 1 mole of any gas at STP. So this is a really useful conversion factor. The molar volume of any gas at STP is 22.4 liters per mole. So for every mole of gas, it's going to occupy 22.4 liters. This allows us to convert between volume and amount of gas at STP. So same number of molecules of gas will occupy the same volume. Which gas it is doesn't matter. Now, the mass of 1 mole of gas will be different. So let's look at that. So here we have 3 gas cylinders, and we filled up balloons. This is helium, xenon, and methane. 1 mole of STP of each of these gases, the balloons are going to be the same size, 22.4 liters. Are those balloons going to weigh the same amount? Nope. 1 mole of helium is going to weigh how much? 4.003 grams. Because it's 1 mole of gas and 1 mole of helium weighs 4 grams. How about the xenon? What's the molar mass of xenon? 131.3. Do you think that xenon balloon's going to float like the helium balloon? No way. It's going to fall pretty fast, actually. It'd be surprising. I don't feel like calculating the molar mass of methane. But you get the idea? So gas densities can vary significantly. You need to remember density is the ratio of the mass to the volume. For gases, because they're so much less dense, instead of grams per milliliter, we usually express them in grams per liter. To calculate the density of a gas at STP, we know what the volume of 1 mole is, and we can figure out the mass of 1 mole. That's just the molar mass of the substance. So we take the molar mass and divide by the molar volume. So for helium, 1 mole would weigh 4 grams per mole. The volume at STP is 22.4 liters per mole. And so these moles cancel out and we get units of grams per liter. The density of helium is 0.179 grams per liter at STP. For nitrogen, 1 mole of it's going to occupy the same volume, but it's going to have a larger mass. And so the density is going to be greater. Any questions? The density is directly proportional to the molar mass. So if you need the density at other conditions other than STP, you can use this equation. I don't use that equation because I don't like having to learn more equations. You get a bunch of letters like that, and it's so easy to get them mixed up. So if you like that, go ahead and use it. This script capital M stands for molar mass. Like we don't have enough M's. Just a regular capital M is moles per liter. But if it's in front of a unit, it means mega. And we've got lowercase m is meter, and MOL is moles, and MI is miles, and yeah. So I'm going to calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius without using that equation, because I don't like it. If you like it, you go right ahead, but I don't like it. So this is how I approach a problem like this. It says calculate the density. So I ask myself, well, what is density? Density is mass divided by volume, right? The mass divided by the volume. Stupid train. So I have a gas. I need its mass and its volume to calculate the density. It doesn't give me any of that in this problem. So this is where we choose something convenient. Let's choose to look at 1 mole of gas, because then I know what its mass is, right? 1 mole of xenon gas, I just use its molar mass. And 1 mole, that's N, with a pressure and a temperature, I can use the ideal gas law to calculate the volume. So choose 1 mole. So the mass of this is going to be 1 mole times the molar mass of xenon, 131.3 grams per mole. You don't actually have to do this part, but I'm just going to show you. 131.3 grams. So that's the mass of this sample that I chose, 131.3 grams. What's the volume of 1 mole at 742 millimeters of mercury and 45 degrees Celsius? I'm going to use the ideal gas law. So when I rearrange that, I get volume equals nRT over P. So N is 1 mole because I chose that. So that's going to be an exact number. 0.08206 is the ideal gas constant, liter atmospheres, per mole Kelvin. And then I need the temperature. Can I use 45 degrees Celsius? No. It's got to be in Kelvin. So 45 degrees Celsius plus 273 318. That's the temperature in Kelvin. Divide by the pressure. What does the unit for the pressure have to be? ATMs. It's given in millimeters of mercury. So you've got to convert that too. 742 millimeters of mercury times 1 atmosphere per 760. Get it together. Millimeters of mercury. 742 divided by 760. 0.976. That would be 3 significant figures. Carry 2 extras. 31 atmospheres. So that's in the denominator here. Look at the units. Moles cancel moles, atmospheres and atmospheres, Kelvin and Kelvin. It's encouraging that liters is left, and that's what we're looking for, is volume. So we got 0.08206 times 318 divided by 0.97631. 26.728 liters. That's the volume of 1 mole of xenon at this pressure and temperature. It's different than 22.4 because we're not at STP. So that's the volume of this gas, so I'm going to plug that in up here, 26.728 liters. 131.3 divided by 26.728 equals 4.9124 grams per liter, and that rounds to 4.91 grams per liter. Any questions? Yes? Where did I get the 760? That is the conversion factor between atmospheres and millimeters of mercury. Any other? It's exact, yes. Any other questions? So this is a different approach than using that equation that the density equals something over something. I don't use it, so I don't remember it. I have already memorized density is mass over volume. I have already memorized the ideal gas law. And so what I'm doing here is I'm just putting 2 things that I already know together instead of learning a new equation. But again, if you like the equation, it works too. So molar mass. For a liquid that's volatile, meaning it will evaporate easily at a low temperature, we can actually determine its molar mass experimentally by converting it into a gas. So we'll take a sample of that liquid, heat it until it becomes a gas, measure the temperature, pressure, and volume of that gas. If we know the pressure, the temperature, and the volume, we can calculate the number of moles using the ideal gas law. And we know its mass because we weighed it. So we take the mass of the gas and divide by the moles, and that will give us the molar mass. So let's do a problem like that. A sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. Well, we can think about the problem and start strategizing first, or we can just take all of those numbers and write them down and organize them first. So I'm going to do that on this problem. So the first one is 827 milligrams, and then we've got 88 degrees Celsius. Oops, I skipped one. Let's just try to go in order here. 0.270 liters, then 88 degrees Celsius, and 975 millimeters of mercury. Those are the numbers, right? Then let's label these. This is the pressure. This is the temperature. Liters would be the volume, and then this is the mass, right? So M, not to be confused with meters. Mass is 827 milligrams. So I've identified all these numbers. And it's saying find the molar mass. So this is where I think, well, what is molar mass? Molar mass is the mass of 1 mole, right? So it's the mass in grams of 1 mole. Well, let's see. Let's just do it this way. The mass of the substance in grams divided by the number of moles. And then we end up with a unit grams per mole, right? So to find that, we need the mass of this gas, and we need the number of moles. Well, they gave us the mass, but they gave it to us in milligrams. We can convert that to grams. So you could write it out like this: milligrams on the bottom and grams on top. Those cancel. Milli means 10 to the minus 3. So we got 1 times 10 to the minus 3. So that's 0.827 grams. That's the mass. So we could plug that in up here. 0.827 grams. We need to find the amount of gas in moles. We have the volume, the temperature, and the pressure. So that's going to be the ideal gas law, right? So N is going to be equal to PV over RT. That's just taking PV equals nRT and solving for N. So pressure, volume, R, gas constant, and T. We always have to be careful about the units here. Is liter a good unit for the ideal gas law? Yeah, it is. The gas constant is liter atmospheres per mole Kelvin. So liters is good. Is degrees Celsius good? No, that needs to be in Kelvin. So let's convert that to Kelvin. (361). Is millimeters of mercury a good unit for pressure? No, the units on the gas constant liter atmospheres. So this needs to be converted to atmospheres. So 1 atmosphere divided by 760 millimeters of mercury. We just use that one over and over and over again. So 1.2828 atmospheres. So now I have volume, temperature, pressure in the correct units, and so I'm going to plug them into my equation. So 1.2828 atmospheres times the volume in liters, 0.270 liters, divided by the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. And the temperature goes down there as well, 361 Kelvin. I have 2 numbers in the denominator. You need to be careful when you do this on your calculator. What I do is I multiply by, this times this, I'm dividing by this, and I'm dividing by that. If that doesn't make sense to you because these 2 things are multiplied, then you need to use parentheses when you put it into your calculator. Put a parenthesis here if you're going to do times, and then you need another parenthesis. Otherwise, you're going to end up with the wrong number. So get your calculator out if you haven't yet, and make sure that you get the same number. So 1.2828 times 0.27 divided by 0.08206 divided by 361. 0.011691 moles. If you get a really, really big number, that's because instead of dividing by 361, you multiply by 361, and that makes it crazy off. Yeah, 3 sig figs there because I had 3 sig figs in the volume, the temperature, and the pressure. So that's my amount in moles. So I take that up here to my molar mass calculation. I've got grams. I need to divide by the number of moles. And there's no room left for the answer. Poor planning. If that's the worst thing that happens to me today, I'll be so happy. So 70.738, which would round to 70.7, and the units are grams per mole. Is that a reasonable molar mass? Yeah. Can you think of an unreasonable molar mass? Negative number. That would definitely be unreasonable. The more gas you have, the more negative its mass. That doesn't make any sense. What about like 0.5 grams per mole? Why is that impossible? What's the smallest atom? Hydrogen. A hydrogen atom has a molar mass of 1 gram per mole. So you can't have a molar mass that's smaller than that. Okay. Here's another example. We are going to do an experiment like this, experiment 5A, and find the molar mass of a volatile gas. So an organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and re-weighs it. Her data is given below. Calculate the molar mass of the liquid. So the way this works is, so we've got this flask, and you put some liquid in it, and you heat it up and it evaporates. When we do this in lab, what we're going to do is we're going to have a piece of foil over that with a little pinhole in it. So as you heat up the liquid, it's going to fill the flask, and when the pressure gets up to 1 atmosphere, well, it's going to push the air out, and the pressure inside is going to stay the same as the pressure outside. It's going to fill the flask. You can measure the temperature and the pressure. The pressure is the same as the atmospheric pressure outside. The temperature is the same as the temperature of the boiling water. You can measure the volume of the flask. When you cool the flask down, you're taking the gas that was in here and you're condensing it to a liquid, and now you can weigh it. So this is the mass of the flask with the gas in it. This is the mass of just the flask. We don't care how big the flask is. We want the mass of what's in the flask. The flask is just the carrier, the holder, the container. It's like, weighing the puppy to give him some medicine. You don't want the mass of you and the puppy, because then you'll give the puppy way too much medicine and probably kill the poor thing. And that would be just like really sad, right? You want just the mass of the puppy. So you subtract your weight. And we understand, we can think about that. But when it comes to flasks and chemicals, some of us just kind of lose our minds and do crazy things, okay? But I don't care about the density of the flask. I want the gas inside. So we need the mass of the gas. So we're going to subtract those two numbers. So the mass of the gas is going to be the 78.416 grams minus 77.834 grams. .582. So that's the mass of that gas. In this problem, we're actually given a particular size. We're not choosing 1 mole. We're given a particular sample. So here's the mass. Again, we're looking for molar mass, so way up here at the top. Molar mass equals the mass in grams divided by the number of moles. So we've got the mass in grams, right? So we can plug that in there. .582 grams. We need to know the number of moles, right? So that's using the ideal gas law. So N equals PV over RT. Just taking PV equals nRT, rearranging. Think about the units on the ideal gas constant, and when we look at these, we see that all the units are not quite right, which is typical. So we need to convert milliliters to liters. We've talked about that. You can do it like I did the milligrams to grams by actually writing it out. Or we can also think, well, milli is 10 to the minus 3. It's moving the decimal point 3 places. The question is which direction. Milli is a smaller unit than liters, and so it should have the larger number. So if I'm going from a small unit to a large unit, I need to make the number smaller. So it's going to be 0.213 liters. 100.0 degrees Celsius. This time, because it's got a decimal place, a 1 decimal place, I want to use 273.15. So that's going to be 373.15 Kelvin with the last sig fig in the 10th place. And then torr. Torr is just another name for millimeters of mercury. So the conversion is the same, 1 atmosphere divided by 760 torr. 0.992. There's my 3 sig figs. 10 atmospheres. So now I have what I need to calculate the number of moles. So the pressure is 0.99210 atmospheres. The volume is 0.213 liters. Ideal gas constant 0.08206 liter atmospheres per mole Kelvin. I know it's tempting to leave those out. Don't do it. And temperature 373.15 Kelvin. Point 99210 times 0.213 divided by 0.08206 divided by 373.15 equals 00690. There's my 3 sig figs. Write down 2 extra digits. That's the number of moles. That's a small number. That's okay. So that's the amount in moles. So that's what I'm going to write in the denominator where I'm calculating my molar mass. 0069011 moles. So 0.582 divided by 0.006911, and I get 84.213, which rounds to 84.2. Units are grams per mole. Is that a reasonable molar mass? Bigger than 1. Any questions? No questions. It's okay.